Section: Introduction. In this section, we discuss how content creators, such as lecturers, greatly appreciate receiving feedback on their work to identify areas of confusion and improve the quality of their content. For instance, when a student doesn't understand part of a lecture, they might ask for clarification on a course forum. Lecturers aim to figure out which part of their lecture caused the confusion to enhance their teaching materials. However, the needs of content creators differ from those of information seekers, like students, who often turn to information retrieval systems, including Q&A methods, to find the information they need. Identifying the root cause of a question can be tough due to several reasons. Questions often lack clear indicators of what exactly caused the confusion. The need for additional information is usually not directly stated. The large amount of content to sift through, and the specialized knowledge needed to understand both the question and the content. For example, a student might ask a question without specifying which part of the lecture they didn't understand, indicating a hidden need for more information. Additionally, lecture transcripts are lengthy, making it hard for lecturers to pinpoint the exact source of confusion for every question they receive. Moreover, understanding some questions requires domain-specific knowledge, as not all questions directly reflect the content of the lecture, adding to the complexity of tracing the source of confusion. To address this challenge, we introduce a new task called backtracing. The goal of backtracing is to identify the sentence in a corpus, such as a lecture transcript, that most likely led to a query, like a student's question. We focus on 3 real-world domains where backtracing can significantly improve content delivery and communication. The lecture domain, aimed at identifying the cause of student confusion. The news article domain, focused on pinpointing what sparked a user's curiosity in a news article. And the conversation domain, which seeks to understand the cause of a user's emotional response, such as anger, in a conversation. We evaluate various popular retrieval systems, including those based on dense retrievers and re-rankers, as well as likelihood-based methods that utilize pre-trained language models to estimate the probability of a query given different versions of the corpus. We also assess the performance of the long context window GPT 3.5 Turbo 16K Chat GPT model, given its capability to process lengthy texts and follow instructions. Our findings reveal that there is significant room for improvement in backtracing across all evaluated methods. For instance, bi-encoder systems often struggle when the query does not semantically match the text segment that triggered it, a common scenario in the lecture and conversation domains. In summary, our contributions in this paper are threefold. We propose the novel task of backtracing, aiming to help content creators improve their work by identifying the causes of queries from their audience. We establish a benchmark consisting of 3 domains where backtracing is crucial for uncovering the context behind a user's query. Lastly, we evaluate a range of popular retrieval systems and highlight the need for new retrieval approaches that consider causal relevance, as evidenced by the challenges we encountered in the modest top 3 accuracy of the best model, which is only 44% in the lecture domain. Related to our work, the field of information retrieval has traditionally focused on finding documents or passages that satisfy a user's information need, with advancements in neural retrieval methods, language models, and the use of pre-trained language models for text ranking. However, the specific needs of content creators, such as understanding what causes confusion in a lecture, have been less explored. Our backtracing task differs from previous approaches by focusing on the language in the content as the context for the user query, offering detailed insights into the linguistic triggers of user queries, unlike methods that rely on observable user behavior. This approach not only aids content creators but also opens new avenues for understanding and addressing user queries more effectively. Section Summary. In this section, we introduce the concept of backtracing, a novel retrieval task aimed at identifying the cause of a query within a corpus, catering to the needs of content creators like lecturers who seek to enhance their materials based on user feedback. We formalize 3 domains where backtracing is crucial: lecture for student confusion, news article for reader curiosity, and conversation for user emotion, evaluating various retrieval systems but highlighting the need for new approaches due to the challenging nature of backtracing. While related works focus on information retrieval for users, our approach targets content creators by pinpointing specific triggers of user queries within the content itself, offering insights distinct from behavioral patterns and question generation tasks. Section: Backtracing. In this section, we explore the concept of backtracing, which we can describe as follows. Imagine we have a collection of sentences, let's say a total of n sentences, and someone asks a question related to these sentences. Our goal with backtracing is to figure out which specific sentence or sentences out of the collection prompted that question. We illustrate this idea with an example where we have a lecture transcript and a student's question, and we aim to identify the part of the lecture that led to the student's query. The best approaches for backtracing are those that can score each part of the text on how likely it is to be the cause of the question, even when dealing with long documents. This is important because often, more than one sentence could be the reason behind the question. If multiple sentences are identified as potential causes, we consider it a success if there's any overlap between these sentences and the ones we predicted. Moreover, we acknowledge that some texts, like lecture transcripts, can be longer than what current language models can handle in one go. To address this, effective backtracing methods must find a way around this limitation, possibly by calling on a language model multiple times. Our investigation into backtracing spans various domains without specifically training models on them, a process known as zero-shot learning. However, we do allow for some initial testing on a small set of examples to fine-tune our approach, but we don't update the model based on this data. This approach is reflective of real-world situations where we might not have enough data to fully train a model but can still make some adjustments. When it comes to establishing a benchmark for backtracing, we've chosen a wide range of domains to demonstrate its applicability and to highlight the common challenges. For instance, in the lecture domain, we use real university lecture transcripts and student comments to see which parts of the lectures confuse students. We've annotated these with the help of two experts, achieving a high level of agreement on which sentences are likely to have caused the questions. This dataset, along with others from news articles and conversations annotated with emotions, allows us to test backtracing methods in diverse settings. Each domain presents its unique challenges, such as dealing with long texts or identifying the cause of emotions in conversations, pushing the boundaries of what backtracing systems can achieve. Section Summary. In this section, we formally define backtracing as the task of selecting sentences from a corpus that are most likely to have prompted a given query, with the aim of identifying the source of confusion or curiosity. We explore ideal methods for backtracing that can provide continuous scoring over long texts, handle multiple contributing sentences, and overcome constraints posed by existing language models' context window lengths. Our work establishes benchmark domains for backtracing across diverse areas like lectures, news articles, and conversations, emphasizing the task's broad applicability and shared challenges. Section: Domain Analysis. In this section, we delve into the structure of our datasets and their relationship with the process of backtracing, which is essentially tracing back to find the cause of something. We start by exploring how similar a query is to its actual cause. To do this, we look at the semantic similarity between the query and the correct cause sentence, alongside the highest similarity the query has with any sentence in the corpus. We also examine the difference in similarity between the correct cause and the highest similarity found. This helps us understand if semantic similarity is a good indicator of causal relevance, which is necessary for backtracing. Our findings show that queries and their true causes are not always closely related in terms of semantics, especially in conversation and lecture contexts. This suggests that just because two sentences are semantically similar, it doesn't mean one caused the other. Next, we investigate where the causes are located within the documents. This gives us insight into how much context is needed to identify the cause of a query. Our analysis reveals that in news articles, causes are often found at the beginning, indicating that less context is needed to identify them. However, in conversations, causes tend to appear towards the end, requiring more context for identification. Lectures show a uniform distribution of cause locations, suggesting a need for a broad context. Interestingly, we observe that different queries can lead to the same cause, highlighting the potential for models to pinpoint common areas of confusion. Moving on to our methods, we evaluate various state-of-the-art retrieval techniques to see how well they can identify the correct cause sentences. We look at both the top 1 and top 3 accuracies to see if the correct sentences are among the top candidates selected by these methods. We also examine the minimum distance between the candidates and the correct sentences. Our methods include both similarity-based approaches, which rely on semantic similarity, and likelihood-based approaches, which use predictive models to estimate how likely a sentence is to be the cause. We employ several pre-trained language models, PLMs, for this purpose, including GPT-2, GPT-J, and OPT 6.7b, as well as a newer model designed for long texts. For random retrieval, we simply pick a sentence at random from the corpus. For edit distance, we choose the sentence closest to the query in terms of edit distance. Our by-encoder method selects the sentence with the highest semantic similarity, using the most effective S-BERT models. The cross-encoder method picks the sentence that a cross-encoder model predicts to be most similar. Lastly, our re-ranker method uses a by-encoder to find the top candidate sentences and then a cross-encoder to reorder them based on predicted similarity. This comprehensive evaluation helps us understand which methods are most effective at backtracing and identifying causes within texts. Section Summary. In this section, we analyze the semantic similarity of queries to ground truth cause sentences across different domains, highlighting that semantic relevance does not always imply causal relevance. We also investigate the distribution of cause sentence locations within corpus documents, revealing varying patterns across domains, such as news articles requiring less context for cause identification compared to conversations or lectures. This analysis underscores the importance of understanding the relationship between semantic and causal relevance in backtracing scenarios. Section GPT 3.5 Turbo 16K. In this section, we introduce a method that takes a corpus with line numbers and a query, then identifies the line number most likely responsible for generating the query. The specific prompt we use for this method is detailed in the appendix. We explore several strategies for ranking sentences based on their likelihood of being relevant to the query. One such strategy is the single-sentence likelihood-based retrieval. Here, we look for the sentence within the corpus that, when considered alone, makes the query most likely. To make the corpus and query more relevant to each other, we add specific prefixes that depend on the domain. For instance, in the cite domain, we prepend "teacher says" to the corpus sentence and "student asks" to the query. The full list of prefixes we use is available in the appendix due to space limitations. Another strategy we examine is the auto-regressive likelihood-based retrieval. This approach considers not just the target sentence but also the context provided by preceding sentences. However, in domains like lecture, where the entire corpus is too large to fit into our model's context window, we cannot always evaluate the likelihood in this way for every sentence. To manage this, we divide the corpus into chunks of 20 sentences and evaluate the likelihood of each sentence within its chunk. For example, if a sentence is in the second chunk, we calculate its auto-regressive likelihood score based on its position within that chunk. We also look into the average treatment effect, 8, likelihood-based retrieval, inspired by treatment effects in causal inference. This method focuses on the impact of including a particular sentence in the corpus on the likelihood of the query. Essentially, we select sentences that, when included, most increase the likelihood of the query. For longer documents, like in the lecture domain, we apply the same chunking strategy as with the auto-regressive method to calculate the 8 likelihood scores. Our results, summarized in tables, show that the best-performing models achieve modest accuracies. For example, in the lecture domain, which contains many distractor sentences, the top model achieves only a 44% accuracy for the TOP3 sentences. In the conversation domain, with fewer distractors, the top model reaches a 65% accuracy for the top3 sentences. These findings highlight the difficulty of measuring causal relevance, which is quite different from traditional retrieval tasks. We also observe that no model consistently outperforms across all domains. For instance, while a similarity-based method like the by-encoder performs well in the news article domain, it does not do as well in the conversation domain. This suggests that semantic relevance does not always equate to causal relevance. Interestingly, in the lecture domain, which involves long documents, the long context model GPT 3.5 Turbo 16K underperforms compared to non-contextual methods like the single-sentence likelihood methods. This indicates the challenge current models face in accounting for context. Finally, we note that single-sentence methods generally outperform their autoregressive counterparts, except in the conversation domain. This aligns with our observation that the location of causally relevant sentences varies by domain, with some requiring little context for identification and others, like conversations, requiring more context to accurately identify the triggering sentences. Section Summary. In this section, we introduce the GPT 3.5 Turbo 16K method for sentence retrieval based on likelihood scores, including autoregressive and average treatment effect, 8 approaches. The 8 method is inspired by causal inference and evaluates the impact of including a sentence in the corpus on the query likelihood. Results show that different retrieval methods perform variably across domains, with single-sentence methods generally outperforming autoregressive ones except in the conversation domain, highlighting the complexity of measuring causal relevance in retrieval tasks. Section 8 Likelihood methods does not significantly improve upon other methods. In this section, we discuss how the 8 likelihood methods don't really offer a significant improvement over other approaches. Despite being specifically crafted to assess the impact of a cause sentence, these methods are on par with simpler, non-contextual techniques like those that analyze single sentences in isolation. This observation points to the difficulties we face when trying to use likelihood methods for evaluating how a hypothetical scenario, represented by a sentence, would influence a query.